So what does a compiler do? The bare minimum requirement for a functional compiler is obviously that it can take a correct input source program, so one that does not have syntactical or semantical errors, for example in C, and the compiler translates this into target machine code that's functionally equivalent, or we say it has the identical semantics. So if we write a C program that calculates 3 plus 4, we want to have a machine code program generated that also calculates 3 plus 4, obviously. Of course, that is not enough for a good compiler. So a good compiler should also not only check if an input program is correct, but also give a programmer a hint. So to indicate if there is an error, what type of error there is in your program, and maybe even how you can fix it. So modern C compilers like GCC or Clang actually give some hints as to what they think might be wrong with your program. Sometimes they're right, sometimes they're spectacularly wrong, and they mess up your compilation process. And of course, you don't only want machine code to be generated, but you want code that is fast or optimized for different criteria. So for embedded systems, you would also want to optimize for other criteria like code size or reducing the energy consumption of your code. And maybe this is even more important than producing the absolutely fastest code you can generate. So when you try to build a larger program out of C source code files, you usually, as we've already seen, split up your code into separate implementation files. So these can be C files, as we've already seen. In a typical embedded program, you would also have some S files. S stands for assembler. So these are files that contain assembler code, which contains instructions that cannot be generated by the compiler. For example, instructions that include privileged operations or set the step pointer, which is not directly accessible from C code usually. So each of these files, as we've seen, is a separate compilation unit. So it's compiled, or for a simpler file, we say it's assembled separately by our C compiler or by our assembler for our target architecture like ARM. And each of these compilations or assembly processes generates a separate object code file. This contains, as we've already seen, relocatable object code. And so, for example, if we call a C function in this file, from here, we have a reference from here to here. So these references have to be resolved. So here's some open link to another function, and the linker just ties up these loose ends and builds an executable, possibly including more libraries like the standard C library or the mathematics library we specified during the compilation process. So if we look at this in detail, so our one compilation process for our C file, we see that this is not just a monolithic compilation process. A compiler consists of several stages, as we've already seen in the introduction. So we first start with the C file we've written. This is being preprocessed. The preprocessor, for example, takes care of including the header files, so of generating a textual copy of your header file inside of an intermediate C file. And this generates just another valid C file. This C file is then compiled by our compiler and very often can generate an assembler file. An assembler file just contains human-readable representations of machine instructions. This S file is then assembled and generates an object file containing the binary machine instructions. Very often modern compilers just omit the stage of generating an S file and calling the assembler, and directly can generate object code files without going through the assembly stages. This speeds up the process quite a bit. So let's first look at our preprocessor here. What does the preprocessor do? So as we've already seen, it imports header files. So it includes textual copies of header files. So you've seen there are two different ways to write header files. So on the one hand, you have these angled brackets here. These angled brackets tell the C compiler that this standard IO.h file is not part usually of your common project that you're just trying to compile, but maybe a system provided file. So there's a search path defined by -i command line parameters usually for the compiler, and there's also some standard search paths included in your compiler. So in these directories, the compiler tries to figure out if there's a standard io.h file, and if there's one, it takes the first one it can find in the path and includes it. When you use double quotes to name your header file, it means it's somewhere in your local project. So it is in your local search paths or even in your current directory. So include files are the one important task for the C preprocessor. The other one is macro processing. So you can do simple text substitutions. So for example, you don't want all sorts of magic numbers to appear in your code, but you want to give them valid names. So instead of just putting a value 42 somewhere, you can define 42 to be the answer. So you can always use a text the answer instead of a value 42, and everyone knows what is actually meant. So the general syntax for this is hashmark define. So this tells our preprocessor we want to define something that's named name, and we want to have it this value. Now value is a bit of a misnomer because it's just a text replacement. So whenever name appears, this value is just copied verbatim into the text at that space where name originally was. But we can do more complex things. So we can define macros. So macros are also just a sort of text substitution. So we can define a macro called max, and by including brackets, it tells our preprocessor that stuff inside the brackets should be replaced. So if we use max bracket 2, 3, closing bracket, it would replace x by 2 and y by 3, and then would replace the whole text by 2 is larger than 3. If yes, return 2, otherwise return 3. So this is just a text substitution. This is not an implementation of a function, even if it looks like being an inline function. So you have to be extra careful. For example, if you write it this way, you can actually introduce lots of errors if x does not just expand to a single number or variable name, but to a more complex function, because it's just a text substitution. We won't go into too many details here. If you're interested, we can give you more links on this. So defining macros can lead to subtle errors which are hard to find. The other thing you can do with header files is to do conditional compilation. For example, you want to build two versions of your program, one that includes helpful debugging messages, and the other one you want to deliver to your customer after you debugged everything. You don't want to delete all these printfs by hand, but you just want to set one switch in your compilation chain and then just omit all these printf messages. And you can do this by ifdef. So ifdef just checks, has there been a define for that name we give after that one, like debug here. So has a symbol called debug been defined for a preprocessor? If so, include all the text until the matching endif. You can also actually nest these into different levels. And so only if debug has been defined here as a constant for our preprocessor using a define up here, the preprocessor actually copies printf, and if debug has not been defined, this printf is omitted, so you don't get any debugging messages. And you can give these defines not only as a define directive for your preprocessor, you can also include it in the command line. So you can call your C compiler GCC, and using -d, you say you define a preprocessor symbol called debug. So whenever you do this, your printf is included. If you omit this debug from your command line, your printf is not included in the program that's being compiled. So the insertion of a header file to C source code files happens as a response to your include statements. You have macro substitutions. You can define a constant to a value of 5. So all references to const will be replaced by the text 5, a character 5. So the preprocessor doesn't know that this is a number. It's just a character for it. And your compiler has to figure out if it's the correct number. The preprocessor doesn't use any type checking, doesn't know anything about C syntax. It's just providing textual replacement here. And that's important because that's the source of lots of confusion and many errors in C code. So for beginning C programmers, I'd recommend Don't use macro functions. Implement stuff as functions. Your compiler is usually intelligent enough to optimize it quite a bit, so your code will run efficiently even if you use real functions instead of macros. Of course, if you look at real C code like Linux kernel source code or stuff like that, you'll find lots and lots of that stuff misused, and you'll find extensive use of the C preprocessor makes your code really, really hard to read. The good thing is you can take a look at what your preprocessor has generated. So if you compile your file file.c and you want to see what the preprocessed C code output is, you give the command line option -e and give an output file name, so it generates a file output.c with all your text substitutions, macro substitutions performed, so you can take a closer look at what this looks like. And for many cases, it's not very nice to look at this because it gets very complex as soon as you include system header files like standard.io. So the next part of our compiler is the compiler itself. So the compiler itself, as we've seen, consists of a front end and a back end. So this front end analyzes the code, checks it for correctness, and if it didn't find any error in your source code file, it generates something for the back end to be used, and the back end then generates your machine code. So the source code is read. It's broken up into basic elements called tokens. It's checked for correctness. If it's not correct, an error is reported, your compilation process stops, so no intermediate code here would be generated. If your compilation process would be successful, your analysis, so you don't find any errors in the code, actually it doesn't generate machine code directly, but it provides a so-called intermediate representation that the backend can use to generate machine code. Now the backend then can do several steps. It can read this intermediate representation, try to apply several optimizations to it, then it translates the intermediate representation to the machine code. So for example, human readable assembler source code for your target architecture like an ARM or a RISC-V, and then it can also again try to optimize the assembler code. So let's look at the front end stages. The first stage of the front end is actually concerned with splitting up your source code into elements that belong together. So this is called lexical analysis or scanning. So your source is just a stream of characters. So it's an I, an N, a T, a space, an X, a space, an equals sign, and so on. But your compiler needs to figure out which of these characters actually belong together to form one symbol. We've already indicated this by colors here. So the first three characters I, N, and T obviously indicate, with the space after it, that we have something to declare an integer variable here. So we split up our stream of input characters using defined borders like a white space or a semicolon or stuff like that. And the lexical analysis just reads our source code and returns the list of the tokens and the type of that token. So it starts reading I, N, and T and reads white space. So it can look up, oh, we have something called int. Int, we can look it up in a table, is a keyword. So something that's reserved in our C language to indicate, yes, we want to declare an integer variable here. So then it reads something else. It reads something called X. And there's a white space after that. So it reads X. It looks it up in a table. It knows it's something started with a character. It's not in its special table of keywords. So it's just an identifier for maybe a function or a variable. It doesn't actually know at this point because the lexical analysis doesn't know a lot about C syntax. Then it continues reading. It reads the equals sign. It knows the equals is always an operator. Then it reads a 3. 3 is an integer constant. Then it reads a semicolon. A semicolon is a special symbol, and so on and so forth. So your code is split according to whatever your preprocessor knows about your language. So in C, it knows about variable names, it knows about special symbols, it knows about integers or floating point or string variables, and it knows about your reserved keywords, and it returns a list of, these lexical symbols and an identification of that symbol, one after the other. So This is a very simple step. This can usually be implemented by an automaton, so finite automaton can implement this, and this is the very first thing we'd also be discussing in our compilers lecture. So, of course, just giving a list of tokens isn't enough, because programs have structure. So now we have to figure out if all the tokens that have been generated by our syntactic analysis, by our lexical analysis, are conforming to the structure we provide in the grammar of a language. So for example, we have a tree like this one here, and we can say a compound statement might be made up by some operators, like assigning a constant value to a variable x here, assigning something else, like a arithmetic expression x plus 7 to a variable y. It might contain a while statement. A while statement has a loop test and a loop body, and so on. So this structure that we also see in our previous line here, in our previous code, this structure is checked if this is a valid structure. So for example, if we'd forget to include the while condition here and would just say while, opening curly bracket, our compiler would complain that something is missing here. So syntactic analysis checks if the structure of your code, of the tokens, actually conform to the grammar of your language. Now, this is not everything a compiler has to do, because you could still try to assign, for example, a string to an integer variable. And that's what's happening here. So, for example, you write int x equals string bananas, semicolon. This is syntactically correct. It's a correct statement. It has a variable declaration here. It has name of a variable, an equals sign, and something else. But obviously it's very difficult to assign bananas to an integer variable. So we need an additional step to actually ensure that the types are compatible here, so that we only try to assign integer variables or integer constants to a variable x, but not a string constant. And this is the task of our third part of our front end, the so-called semantic analysis,